All right, so welcome to part 2 of Wednesday's lecture. We're going to be continuing on with chapter 6, moving on to 6.9, electric potential energy. All right, so if you recall from chapter 3, the electric force is equal to 1 over 4 pi epsilon naught, the constant, Q1, Q2 divided by R squared. So notice that I have not put a vector sign over this, so we're looking at the scalar electric force. It can be positive or negative, but I've not added the directional component. Also, 1 over 4 pi epsilon naught is equal to 9 times 10 to the 9 Newton meters squared over Coulomb squared. Okay, so using this expression here and the negative gradient of potential energy, you can get electric potential energy. So Physics 2, you're welcome to prove this to yourself, but it's optional. Electric potential energy is equal to 1 over 4 pi epsilon naught Q1, Q2 over R. So dissecting this problem, we can see that it's going to depend on the charges, which could be positive or negative for either one, and the distance between them. Now remember, electric force can be positive or, electric force can be repulsive or attractive. So gravity is only attractive. And so there's no minus sign in this equation because the minus sign is going to be dictated by the charges. So in a repulsive situation, so that would be not like gravity, if we were to look at the potential energy with respect to R, we would see a relationship like this. And for an attractive electric force, we would see something that would look a lot more like what we saw with gravity. And so this is what's going to happen to the potential as two objects, space between them changes. Okay. So let's go ahead and do an example with electric potential energy. So we'll do ionization energy. So a certain amount of energy, and we'll get more into this in chapter 8, but for now, we'll start here, is required to remove an outer electron. And when you remove an electron, you of course ionize the atom and it becomes, of course, here's where I've got two physics jokes and here's one of them. So one atom says to another atom, dude, I think I lost an electron. The atom's like, oh man, bro, are you sure? I'm positive! Because of course if the electron is removed, it is now positive. Ha ha ha, groaning laughter, insert here. Okay, so we have a positive ion with charge plus E. So minimum energy required to remove one outer electron is called ionization energy. So remember, the radius of an atom is approximately 1 times 10 to the minus 10 meters. So let's estimate this energy. in joules and convert it to electron volts. All right, so this is just an energy principle problem. Our system is the two particles. So we have the outer electron and the ion, which has charge positive E. The surroundings, so remember with electron potential energy, electric potential energy, we don't need mass, we just need charge. So whatever caused this, so the cause of ionization. We don't really need to know what it is, only that it happened. So something did work on it. So the initial state, they're bound. And in the final state, they're unbound. So the electron has been freed from the atom. Okay. And so we're going to make a couple assumptions to go after this estimation. So we're going to assume that the initial kinetic energy of the electron is equal to 0 and that the energy input is work. So E initial at rest. Okay, so this is our problem. Now we're going to move on to our energy principle setup. The final energy is equal to the initial energy plus any work done to it. So expanding this out, we would have the kinetic energy of the ion plus the kinetic energy of the electron final plus the mass initial c squared plus the mass of the electron c squared plus the final potential energy between them is equal to the kinetic energy of the ion initial plus the kinetic energy of the electron initial plus the mass initial c squared plus the mass of the electron c squared plus the potential energy between them. So, a couple of things. We want to find our zeros. Now, I said nothing about anything being in motion. So the kinetic energy of the ion is 0. And the kinetic energy of the ion initial is equal to 0. There has been no identity changes. So let's go ahead and recognize that these two terms are not going to change. So they'll cancel out on both sides. Also, speaking of kinetic energies, it's pretty safe to assume that, so we said it started out initially at rest, and to really go after this approximation, we can also just assume that the electron is at rest at the end. So all we are dealing with then there's work, is we're dealing with the potentials between them as well as the work. So let's go ahead and rewrite. So work is equal to the final potential minus the initial potential. Okay, so work is equal to 1 over 4 pi epsilon naught Q1, Q2. Now, in the final state, we said they're very far away. So what we're essentially saying is that R is approximately infinity. They're so far away that it is dropped to negligible. So minus 1 over 4 pi epsilon naught Q1, Q2, and this is an outer electron, so initially we had the radius of an atom as the distance. So this term is basically 0. They're far away. They don't have any more potential between them, or any more potential that's worth measuring. So the work between them is equal to minus 1 over 4 pi epsilon naught positive E times minus E divided by the radius of the atom. Work is equal to 9 times 10 to the 9 Newton meters squared over c squared. So this is radius of generic atom. 1.6 times 10 to the minus 19 coulombs quantity squared over 1 times 10 to the minus 10 meters. So let me say a quick thing about the sign. So I see that we've got a positive here and we've got two negatives. So our overall answer is going to be positive, and that's what I've done here is I've decided to just say our overall answer is positive. Based on this reasoning, therefore, I'm just going to square 1.6 times 10 to the minus 19, and I'm good to go. All right, so the work is equal to 2.3 times 10 to the minus 18 joules. And now we want to convert that into electron volts. So work is equal to 2.3 times 10 to the minus 18 joules times 1 eV over 1.6 times 10 to the minus 19 joules, which is equal to 14 eV. So ionization energies for random nondescript atom, we're looking at around 14 electron volts. So keep that in mind when we get to chapter 8, where we'll look at this in a little bit more detail. All right, so moving right along, I think you're getting a good taste for just how powerful and cool the energy principle is. So 6.10. So for this particular section of your book, I'm just going to highlight a couple key points that will be important later. I'd really recommend taking the time to do a deep read. There's a lot of plots in that section, which I'm not going to reproduce since your book does such a good job of it. But I want to make sure that I highlight a couple key points that I want you to make sure that you've taken away. So if we look at potential and kinetic for a gravity system, so say the probe plus dysnomia. So what I'm going to plot out here is I'm going to put energy on the y-axis, and then I'm going to put distance on the x-axis. So we could say maybe you're sorting out initial and final for that particular problem. So let's look at the kinetic energy. So in our initial setup, we had a lot of kinetic energy, and we saw that it started to decrease as the gravity from dysnomia sloped the probe down. And then we started out with not a lot of potential, and then we can see an increase as, or we started out with, not a lot of potential, very negative potential, and we saw that as we got further away, we started to approach 0, and it became less negative. Now, you could look at a line here where you're summing the kinetic energy plus the potential energy. And what you would find if you were to add kinetic and potential for this whole situation, so K plus U, is that it would be constant. It wouldn't change the entire time, which makes sense with the conservation of energy. As you gain kinetic, you lose potential. As you gain potential, you lose kinetic. Energy is a conserved quantity, and this is one of the consequences. And of course, this isn't a case with, negligible work. So for this case, kinetic energy final plus potential energy final is equal to kinetic energy initial plus potential energy initial. And we can see that graphically here. So as the probe gets further and further and further away, eventually the kinetic energy is going to reach a point where it's essentially the same as k plus u. And what that implies there is that the potential energy has reached the point where it is essentially zero. And this is possible for a system that is known as an unbound system. So basically, you can become free of the system. The probe isn't going to start to orbit dysnomia. It's actually going to break free of the gravitational hold that dysnomia has on it and escape the system. So K approaches and becomes essentially for unbound system. So separation can increase without bound. This will get more and more fleshed out as we go deeper and deeper and deeper into the energy principle. But just for now, this is the key concept from this particular setup. So in order for this to happen with our example of dysnomia and the probe, it had to have sufficient velocity to escape the moon. So we've all heard about the escape velocity before. We've got an escape velocity from Earth that NASA had to overcome in order to send the first probes into space. So, and just a quick note, when we're thinking about this, kinetic energy can never be negative. We've seen that potential can be negative, but kinetic energy can never be negative. So note further that because kinetic energy is approximately 1/2 mv squared, so mass can never be negative, and velocity can be positive or negative, but if you square it, it's always positive. Further, we've also seen the expression kinetic energy is precisely gamma mc squared minus mc squared. Gamma is always greater than 1. Always, sometimes it's just not much greater than 1. So once again, we see that we will always have a positive kinetic energy, and this places a limit on motion. So if I ever see a negative kinetic energy on an answer, something has gone wrong. Okay, so I've talked, so we'll end this little note. All right, so going back to bound and unbound systems, an example of a bound system would include Earth orbiting the sun. So when we're looking at planetary bodies, if an object gets trapped into orbit, it's in a bound system. So when we send a satellite up into space, we don't want it to reach escape velocity. We want it to orbit around the Earth, so we want to keep it bound. By the way, when we talk, so we introduced a little bit of quantum mechanics in Chapter 8, and this will start to throw all of this on its head and really give you a deeper and really beautiful understanding of bound and unbound systems. All right, so just one more note on this. On your own, do the examples of making an energy graph. Okay, so moving along. Actually start fresh paper for this one. So I told you that there is an escape speed from Earth, and we can use the energy principle to understand it. And this is the speed required to become unbound. So which is of course related to the energy required to break free, which is a great Queen song. I want to break free, become unbound from this system. Give me kinetic energy. For those of you in choir, I apologize. All right, so the minimal condition for escape is going to be that k plus u is equal to 0. So let's start breaking this down and go after escape velocity. So ki plus ui is equal to 1/2 mv squared escape plus minus gmm, mass of the object you're trying to escape, mass of the object that's trying to escape, divided by the distance between them, is equal to 0. This is, of course, for a classical system. V is much, much smaller than C. And so we can use this setup to calculate the escape speed for a given object. And we're going to do this for Earth because, that's the most relevant to us. So for Earth, so we'll set this up. System is going to be Earth plus a rocket, because that's the object most likely being used to escape. The surroundings would be nothing. The initial state, let's make it easy. At surface with some non-zero velocity. And the final state, very far away, nearly at rest. Okay, so setting up our energy principle, we have the kinetic energy of the rocket final plus the kinetic energy of the Earth final plus the potential between these two objects final is equal to the kinetic energy of the rocket initial plus the kinetic energy of the Earth initial plus the initial potential plus any work done. So where are my zeros at? All right, so we've said the rocket is essentially at rest. Just like in our previous problem where we talked about dysnomia and Eris essentially being fixed in space, it's true the Earth is moving, but it's not going to move noticeably in this length of time. So we're going to go ahead and set that equal to 0. And by our original conditions that we said that k plus u is equal to 0, the potential between the two of them, they're very far away, is essentially 0. Okay, so what we have here, now that we've got all of our zeros, this side is now zeroed out entirely. Oh yes, and there's nothing in the surroundings, so work is also equal to 0. Always, always, always make your life easy. So 0 is equal to the kinetic energy of the rocket initial plus the initial potential between the Earth and the rocket. Okay, so now we're ready to flesh this out in more detail. So 0 is equal to 1/2 m rocket vi squared plus minus g m Earth mass rocket over our initial. Oh, and in the original setup, since we know there's no identity change, I just didn't include rest mass energy. So the initial velocity is equal to 2 times the gravitational constant times the mass of the Earth divided by the initial radius of the distance between the two objects, which is equal to Earth's radius. We can see we have the mass of the rocket in both those terms, so we can just divide that out. All right, so let's plug in for our own planet. So we've got 2 times 6.0 7 times 10 to the minus 11 Newton meter squared over kilograms times 6 times 10 to the 24 kilograms divided by 6.4 times 10 to the 6 meters. And so the escape velocity from Earth, assuming absolutely perfect conditions, is equal to 1.12 times 10 to the 4 meters per second. Of course, this neglects friction, air resistance, etc. So you have to be going at least that fast in order to escape the planet. So, and there's some really interesting and fun equations you can do with rockets, because rockets will undergo an identity change in the process of escaping Earth because they're dumping fuel at such an incredible rate. So they're fun. They're fun problems. They're fun problems you do in, if you were to take a classical mechanics class beyond the Physics 1 sequence. So it's like typically it's a 300 or 400 level class. We don't offer it here, unfortunately. All right, so bound and unbound systems. Just to kind of summarize, so if k plus u is less than 0, you're dealing with a system that is bound, or if it's limited to this. And if k plus u can reach a state where it's greater than or equal to 0, system is unbound. Okay, so moving along to 6.11. By the way, chapter 6 is the longest chapter we do. So just some final thoughts on potential energy to take with you. So potential energy depends on separation between pairs of objects, not position. What matters is how far apart they are, not where they are. Potential energy must approach 0 as separation becomes large. For attractive interactions, so Joey-Tribbiani interactions, the potential is negative as distance decreases. So it'll get more and more negative. So that really does work for the Joey-Tribbiani example. The opposite happens for repulsive interactions. Come up with your own funny antecedent there. And one more thing to note, potential energy is path independent. So what do I mean by that? So this is a concept we're going to really build on several times throughout this course. Those of you who have taken Calc 3, you'll have definitely seen mathematical explanations of path independence. We're not going to do those in this class, but essentially, if you have a particle that's going to travel from A to B, so it's going to get from here to here. The change of potential is going to stay the same if it does this, or if it does this, or if it does this, or this. It doesn't matter. All we care about is that change. How it got there is irrelevant. Only where did you start from? Where did you end up? That's what matters. I'm sure you could come up with some poetry some poetic life advice based on that. But delta U depends only on separation. So any path gets the same numeric result. UB minus UA is constant. And that's true for each one of those paths, in which case you say, where'd you start? Where did you end? The end. All right, so a special case of path independence is a round trip. So when you look at a round trip, so let's say I start here, and I go over here, and I go over here, and I go over here, and I come back to where I started. What's my change in potential? In that case, delta U round trip, and I think you're already there, is equal to UA minus UA is equal to 0. If all you do is end up from where you started from, your change in potential is 0. And that means no work happened. So these are some key concepts that I want you to have to understand potential energy as we move forward towards more and more complicated systems. All right, so that wraps up chapter 6. So the last thing I want to do is just to set us up for next week. I'm going to just briefly talk about chapter 7 and what you can look forward to. And that way we can start Monday's lecture with a rather long example that I don't want to start today. Okay, so now we're going to crank it up a notch, and we're going to look at extended objects. So, and your quiz will only have chapter 6 on it. So, if you think back to chapter 4, we have previously introduced extended objects. So, they're not point particles. So shape matters. And because shape matters, they can be stretched, compressed, and generally deformed. And all of this is going to expand the way we think about the energy principle. So we have previously used the ball spring model of matter. So think vibrating matter. Just a pretty accurate thought model. And we use this to do things like speed of sound, tension, and compression forces. So all of this comes from this model. So we're going to expand this model and use it to understand temperature. Which will further increase how we think about energy, because, it should come as no surprise, temperature is related to energy. And so we can do this by thinking about if atoms are moving, they must have kinetic energy. All right, so that is all I wanted to say about chapter 7, and I hope that you've enjoyed these first round of lectures as much as is possible, and I will have more up next week.